Okay. Previously, we've looked at exo and endothermic reactions in terms of what temperature changes they would cause. So we talked about how in an exothermic reaction, the reaction releases energy to the surroundings, and so the surroundings get warmer, while the reaction itself is actually losing energy. So the transfers from the reaction to the surroundings, so it feels warmer. In endothermic, we have the opposite. The reaction is absorbing energy from the surroundings. Therefore, the surroundings lose energy in the form of heat and will feel colder. So that's sort of how you can test it experimentally, is actually by measuring temperature changes. You can actually figure out if a reaction will be endo or exothermic, and we can actually figure out what this value of delta H will be without actually carrying out an experiment. We can do it if we know about the chemical bonds that are being broken and are being formed, because we said every chemical reaction involves the breaking of bonds and the forming of bonds. So what we're going to do what we're going to use to do this is we're going to use values called bond enthalpies. Really, we can also call these bond energies. The bond enthalpy is the energy required to break a bond. Now, technically, it's this thing called a mole of bonds, which is like a really big number of the bonds, but that's not so important for us. We have a data table that we're going to use that lists how much energy it takes to break every single kind of covalent bond that we've been looking at. Okay? These bond enthalpies, therefore, are basically a measure of how strong the covalent bonds are. The stronger the bond, the more tightly the atoms are joined together, and the more energy it takes to break the bond. So if you see a higher bond enthalpy value, that means it's a stronger bond. And so now we're going to use these values to calculate the changes in the reaction. So like we looked at before, we said that every reaction was, if I go back here, was the breaking of bonds followed by the forming of bonds. So if we can add up all the energy that we have to put in to break all the bonds, that will give us this amount of energy. And then if we can add up all the energy, all the bonds that we're going to form and figure out how much energy that is, the difference between those two values will be this value, the delta H. So that's what this equation is telling us here. What we need to look at is how much energy do we have to put in to break all the reactant bonds, and then we have to add up how much energy will we get out when we form all the product bonds. And the difference between those two, so minus, the difference between those two will tell us what's the change in energy for the reaction. So this is an example here where we've actually drawn everything out for you so we can follow through. So this reaction is between nitrogen and hydrogen forming a product of ammonia. So we draw out all the molecules first so that we can see the bonds. An N2 molecule, if I drew in all the dots, would look like that. There's a triple bond between the nitrogen atoms. Hydrogen molecules have single bonds between their atoms, but there's 3 of them in this reaction. That's why it's been drawn 3 times. In the products, there's something called NH3 or ammonia. And ammonia has an N with 3 single bonds to 3 hydrogen atoms. Because of that 2 in front, I need to draw that molecule twice. So what bonds have to be broken for this reaction to take place? Well, I've got to break 1 triple bond between the nitrogen molecule, and I've got to break 3 H to H single bonds, so 3 times H to H. So now I just have to look those values up. Now right here we've given them to you, but I'll show you the data table for the next example. So it takes 945 kilojoules of energy to break the N-to-N bond, that triple bond. It's very, very strong. And then we have the H to H bond is 436. So that one gets multiplied by 3 because we're breaking 3 bonds, 3 hydrogen molecules apart. So if we add this up, these 2 values, that's the energy to break all the bonds. So 945 plus 1,308, it takes 2,253 kilojoules to break all the bonds. Okay, now I look at the products. The products have, each molecule has 3 N to H bonds, but actually since there's 2 molecules, in total there are 6 N to H bonds that I need to break. 1, 2, 3, 4, 5, and 6. So there's 6 different bonds to break, but it's all the same value. So the N to H bond has a bond energy value of 391. So 6 times 391 is 2,346. Okay, so remember that we're putting in the energy to break the bonds. So I have to put in 2,253 kilojoules to break all the bonds. And then from there, I get out 2,346 kilojoules when the bonds are formed. So I can see that the amount of energy involved in the formation of the bonds is bigger than the amount of energy in the breaking of bonds. And so when we have that situation, we'll end up with a net change that's actually negative, because I had to, the amount going up is smaller than the amount going down. So I know that when I'm done, I should end up with a delta H value, the change, and the change should be negative. So all I have to do is take the bonds, the energy from the bonds broken, 2,253, and subtract the energy from the bonds formed, 2,346. And the difference is minus 93. And so that is the value here. The value of our delta H is negative 93 kilojoules. And because it's negative, that means this reaction is exothermic. So it's negative. The reaction itself is losing energy. So where does that energy go? It exits. It exits exothermic, and it goes to the surroundings. So this reaction releases energy to the surroundings. It releases heat to the surroundings. Okay, here is what this table looks like. This is from the DPIB chemistry data booklet. So if we want to find a particular bond, we have to match up 2 elements. So like in this one, we're going to look at a C to H bond. So there's C and there's H, and so I find where they meet. So the value for the C to H bond is 414. If I need to find multiple bonds, like double and triple bonds, I'm going to have to come over here to the multiple bond table. So at this point, you should pause this one, and you should start working on question 1, because some of these, like A and B, we already know how to do. And then you're going to be trying C and D, and you'll see if you can solve this question. I'm actually going to stop this video now. You can try it, and then I'll make a solution video.